So the problem that I'm going to solve today is the vehicle routing problem. It's a problem that we haven't covered in class, but it is a very important problem in linear programming. So the vehicle routing problem is a generalized version of the TSP, which is the traveling salesman problem, and it basically tries to minimize the distance that a traveling salesman goes across cities. The VRP is a little bit more complicated in the fact that you have multiple vehicles, so you have basically multiple traveling salesmen, and you also have a limit on your quantities that your vehicles can have. So the main goal of the vehicle routing problem is basically maximizing your efficiency of your logistics company by minimizing cost. So the main idea is that vehicles have to make deliveries to customers in different cities. So when you're making a logistics company, you're gonna have 4 or 5 trucks, you're gonna have 10 or 15 cities, and you're gonna have to minimize something to maximize your profits. So either it be minimum distance, minimum time, minimum amount of vehicles. There's a bunch of different variables that you can have minimized into this. So the VRP started in 1959, and since the 1960s, a bunch of companies are using the VRP to basically maximize their profits. Before World War II, none of this mathematical analysis was performed, and it's just been increasing profits ever since for all the companies. So the VRP is essential because if you have 15 cities that you're traveling to and taking deliveries, you'd say that you have n factorial over 2 destinations or routes to all these different cities. So if you have 15, that's over 630 million routes that you can have. And 630 million is a very big number to minimize and to find the optimal solution or a feasible solution for your objective. So the problem that I focused on today was this focus problem. So you have 6 customers and they want deliverables. And each customer has different demands. They have, let's say, the first customer wants 50, and then the second customer wants 75 units of your deliverable, and the objective is to minimize your miles driven. So each car can carry around 120 units, so that's the carrying capacity of the car. And the array, so the distance from your depot, so like your main node, like your supply node, and then your first customer is 30, and then 30 miles. And then from 1 to 3, it's 20, 1 to 4, it's 10, 1 to 5, it's 10. Then from node 2 to node 4, so let's say when a delivery truck is going from node 2 to node 4, it go 20 miles difference. And then node 2 to node 5, 35-mile difference. So this matrix that you see here is the distance in miles of all the locations that you're planning to go to. So here is the deliverables amount that each customer wants. So the first depot is obviously your node, so you're not going to have any deliverables. And then the second one is 50, the third one is 75, and so on. So going into the problem statement, the problem has to be determined if it's feasible or not. So if each car can carry 120 units, you have to check the sum of all these and see if it's over or under 120, and then if you can have 1 car. And if you're going to have 2 cars, and you need 240 units, and so on. So the sum of all these deliverables is 335 units. So divide the number of units by the carrying capacity of the car, and then you have the amount of cars that you need. So doing that, it'd be around 3 cars, and you need minimum 3 cars for this project. So using 3 cars, we're going to minimize the amount of miles driven, so we're not going to minimize the amount of cars that we need. We're going to have to start adding constraints to our mathematical formulation. The first constraint is going to be to our objective variable. And the objective variable is going to be x, I, j. And it's going to be from 0 to 1. It's going to be a binary variable, because if it's 0, that means that we're not going to that in our root. No root. If it's 1, it's going to be on our root. The objective function is the sum of all the nodes times the cost. So the cost is, in our problem, is going to be the amount of miles that's driven, because we're going to minimize the miles driven. So C is going to be the cost, and X, as stated before, is going to be the objective variable. So we're going to add a constraint so that the vehicle only goes to each house once. So we're going to have only, it doesn't make sense for you to go to node 2 twice if you're only delivering it one time. So it's going to be just adding miles to your total miles driven. So we're going to make a limit so that when you go to a node, you leave it and then you don't come back. So you're only going to be there twice. I mean, you're only going to go in and out twice. So it's going to be that constraint. We're going to make it sigma x. Because going from node 2 to 3 and then leaving 3 to 2, it's going to be the total is going to be 1 and 1, so it's going to be 2. Since the pizza shop is included on 3 different routes, so you're going to have your car go, make a deliverable, and then come back. So each time with each car, you're going to have, if this is your node, you're going to have 1, 2, 3 routes, and then you're going to come back 1, 2, and 3. So it would be 3 times 2, so you're going to have 6 total node in and outs for your first node. So we're going to make a constraint so that 6 edges actively appear into the supplier. So we're going to make a constraint that sigma x 0j or sigma x 1j is equal to 2m. Because this can be for m amount of cars that you have, but since our problem has 3, it's going to be 6. So initially solving for our problem, we can just do a check. We can just do a guess and check of solution. We're going to have 3 different routes, so we're going to have 1, 1, 1. And our first solution is going to be 1, 2, 3, 4, 5, 6, 7. So notice that until now we haven't done anything with respect to the constraints about the deliverables that each car can have. So we need to check to make sure that this solution is feasible or not, because if it's not feasible, that means that it's overbearing on deliverables. So 2 plus 3, it's going to be 50 plus 75, it's going to be 125 units for this one. And 125 units is already greater than the amount of units that a car can bring. So obviously 1-2-3-1 is not a feasible solution, therefore this solution is not feasible at all. So we need to add a constraint so that this doesn't happen again. And the constraint that we're going to add is going to mean that x doesn't have, like, a path that we're doing does not have a path from 2 to 3. Because if it's doing 2 and 3 in the same path, that means that we're going to have 125 units, and it's just not going to work out. So we're going to have x23 is less than or equal to 0. Because, as I said before, it's going to have too many units. So adding that to our main function, it's going to be, our main function is min Cijx subject to, our constraints are going to be sigma x 1j equals 6, and then our new constraint is going to be sigma x 0 x 2 3 is less than or equal to 0, and then we're going to have x ij 0 1. It's a binary variable. And then we're going to check if our next route is variable after our next route is feasible after adding that constraint. So another solution that we get after running AMPL and plugging this in is going to be 1-2-4-1, 1-3-5-1, and then so on. So we need to check if this route is again feasible or not. So 2 plus 4, we know it's 2, we know it's 4. 50 plus 80 is 130. So 130 is greater than 120. And therefore, the solution is again not feasible. So we're going to need to add another constraint so that a path from 2 to 4 is not existent. So it's going to be sigma x 2 to 4 less than or equal to 0. After adding this constraint, this is our linear program so far. And then running this into AMPL, we're going to get another solution that we're going to have to check is feasible or not. And that solution is going to be 1-2-7-1, 1-4-6-1, 1-3-5-1. And those are our 3 routes for our 3 cars. So checking if this is feasible or not, 2 plus 7 is 2, and this, it's going to be 80, 4 and 6 is 110, no, I'm sorry, 120, and then 3 and 5 are, they're all feasible. So then, checking an AMPL, the objective the output of AMPL is the objective variable amount. So the objective variable amount in AMPL is 175, and this is miles driven. AMPL solves the problem using the simplex iterations, and my option solver for AMPL was Gurobi, and then running Cplex also gave the same 175 miles driven. So, in conclusion, the vehicle routing problem is shown here. It's relatively straightforward. You have to add constraints to subtours. So these constraints right here are called subtour constraints, because you're limiting the subtour possibilities of the vehicle routing problem. So this right here is not a subtour constraint because this is a basic tour constraint because you need your cars to come back to the supply chain. And similar vehicle routing problems are used in